Flora Robotica is a 4-year project funded under the Future and Emerging Technologies programme. The project assembles a highly diverse cross-disciplinary consortium of partners with expertise spanning biology, robotics, computer science and architecture. Our vision is to grow architecture from symbiotic interactions between plants and robots. This is ground research aimed at expanding insight into the cross-disciplinary field of biohybrid systems. We target plants because they're an exemplar of self-organizing, distributed systems that can accumulate material for free through resource sourcing, resource distribution, and resource balancing, whilst maintaining a positive environmental impact. From a robotics perspective, we're investigating decentralized and distributed control to be able to build resilient systems with the capacity for emergent behavior. The prospect of architecture that couples organic and artificial life presents a number of challenges to orthodox approaches of architectural design and construction. Living architecture challenges the idea that we can make complete determinations in advance. It challenges the idea that we can operate with a pre-specified inventory of materials and parts with known performance. It also challenges the notion that as architects we design endpoints that we consider to be completed once construction has terminated. And it also presents a challenge in the translation of high-level architectural objectives and intentions into low-level instructions for self-organizing systems, and also the degree into which we allow emergence of those low-level systems to feed back up the chain of design intent. Our first approach in the project is to steer plant tropisms using environmental stimuli. Our predominant focus is on phototropism. We have artificially evolved robotic controllers to direct growth paths to specified target points, with near 100% accuracy. An additional approach is to directly sense the plants. Sensing channels include transpiration, sap flow, and electrophysiology that allows environmental impacts to be read in real time. This opens the possibility of creating closed-loop systems, where a plant can be trained through feedback, in this case to turn a light source on and off at will. The further approach is to use scaffolds as supports for both plants and robots, with the additional architectural benefit of being able to mark out an organized space. We focus on braid and related interlacing systems, which allow engagement across engineering or handcraft production. They allow for the spanning of vast length scales, and they're materially agnostic, allowing production with synthetic, natural, or mixtures of material. This makes these interlacing systems highly versatile and opens up a rich design space. We've been exploring how these systems can be actuated, how they can be materially graded to achieve specific performance, and how they can be controlled in efficient ways that exploit principles of continuum bodies for new forms of robotics. Through handcraft, we've developed tacit understandings of how to achieve complex topologies and morphologies in braids. And, of course, as architects, we've sought to formalize these understandings in principled ways so that we can explore these systems and their adaptive potentials through representation. This includes simulation-based methods that feed into understandings of how to specify mechanical performance and also material differentiation. The underlying computational methods breed new aesthetic opportunities, allowing us to explore a spectrum from the wild and the self-organized to the cultivated and the predetermined. Within this aesthetic range, we're mindful that plants can contribute to underlying performance capacities by treating them as future stiffening filaments once they've been directed into place and matured. So how does this work extend the prior art? Well, in contrast to manual approaches of directed plant growth to achieve architectural structures, we're contributing insights into autonomous control methods. Where scaffolds have been deployed to train growth, as in the case of Mitchell-Joachim's tree fab hab, or these scaffolds becoming incorporated by growth, as in the case of Bau Botanic, we're expanding the scope of scaffolds by giving them agency and potentials to morphologically adapt over time through artificial growth. So how does this come together in terms of architectural proposition? This is very much work in progress and is more focused on establishing workflows. But as an example, here's a site that we analysed to determine a plane in space with light conditions suitable for a target climbing species. We artificially grow a wild supporting structure underneath this intended canopy, and we skin it with an interlaced weave, which is then further analysed. It's analysed in terms of its structural performance and the light affordances that it gives to be able to determine ideal growth paths, which are then simulated to explore the dynamics of the structure and the architectural opportunities that occur over this growth career. We're also speculating on an artificial version of the Wood Wide Web, where surrounding species marooned within oceans of hard landscape can act as organic management systems of artificial stimuli located on the structure. So this is where we are, and if you need further information about the project, please visit our website. On the website you'll find all journal and conference papers that have been published so far, as well as the reports that we're required to produce as part of the funding.